Good evening. What could be better on a Friday night than a little bit of chemistry, specifically ASMR chemistry? I have a few plans for tonight. I've got not only my usually do paper with calligraphy pen and India ink, but I also have some molecular models. I also got some gym chalk out, but I'm not going to do the usual gym chalk crumble that people do. I have another plan for that. And I also have some cards, some periodic table cards. So lots of possibilities here. And of course, let me know if there's anything specific that you would like to see. And I'm just realizing now that I don't have the chat up, so why don't I get the chat so I can see you if you're there. All right, cool. So I'm thinking, why don't we start with the model kits? No, I have something better. I think we need some candles because it's nighttime and I really like candles. So I think that's the best place to start. So this is the deal, is that my candles are a bit deep, so I'm gonna have to use, check out this match, like, wow. All right, so I'm gonna get some of this phosphorus going here. And use it to, oh, please don't go out, don't go out, okay. And light this thing. So most of these candles are, just regular wax candles, but I do have one that is this wick that's wooden wick. I don't know if you've heard of those. They're pretty cool, but they're also kind of loud. So I haven't decided if I want to get that thing rolling or not. So we'll get this cruising, and I'm going to hold off on the wooden wick one. So how are you all doing? Let me know. What are you up to on Friday? And why the heck did you join this channel doing chemistry? I know why I'm here. I'd love to know what you're up to. Okay, so we got some candles, and next up, molecular models. So there's a really cool company called Mega Molecules, and not only do they have kits, these model kits that I like, but you also get this kind of I wouldn't call it a cheat sheet, but it reviews things about VSEPR theory. So I was thinking that it might help us to have this off to the side and build some of these and remind ourselves, what are these things? So this kit, this is the advanced one. We're going to go advanced. reason why they call these advanced is because they've got not only all of the pieces that we would need for organic chemistry, including the carbon centers, the tetrahedral carbon centers, but we also have some of these that are a bit larger, more complicated. For example, we've got this one that is Trigonal Bipyramid. So we can create a lot of interesting molecules that go beyond the scope of some of the normal ones. So in other words, this kit basically does everything. So that's what we're going to do, is just think about the number of electron pairs in the bonds, and then the number of lone pairs there are, and then what kind of structure you get. So, since I pulled up this Trigonal Bipyramid randomly, why don't we start with this one? And let's look at what this is referring to in terms of how many electron pairs are around it and how many lone pairs there are. So in this case, we've got this central atom. I'm going to move this out of the way. We've got just put it down here for now. Okay, central atom. And in this case, Phosphorus Pentachloride. And I think, this is very rare for me. Usually I have a calligraphy pen. I'm going to get an actual pencil. Oh my god. It's kind of exciting day here. Let's look at phosphorus. I need to get this more in the middle. Okay, phosphorus pentachloride. So, when we have phosphorus pentachloride, that means that if we were to draw out the Lewis dot structure of this, then the phosphorus would need to have 5 chlorines around it. And that might seem a little obvious because there's 5 there, but this is pretty significant because what it means is that phosphorus has an unusual number of electrons around it. So let's see what this means. So I feel like that pencil is not dark enough. I want a darker pen, so I'm going to get something else. Let's see if this one is better for us. Phosphorus pentachloride. I think I can do even better than that, but this is good enough for now. Okay. So our phosphorus, if we do this Lewis dot structure, it's got 5 bonds. start out with showing this phosphorus with just 4 chlorines to get our bearings, because if it had 4 chlorines, it would have how many electrons around it? It would have 2, 4, 6, 8. It would have an octet. But this phosphorus has 5 chlorines. So there's another one in there. We gotta squeeze it in. So we put it in somewhere, and honestly, you can put it anywhere you want. Because right now, we are not drawing the structure, but rather we are just counting up the electrons that are there. Okay. So right now, this phosphorus has how many electrons around it? It's got 10. So it has expanded its octet. Yeah. And it can do that. Phosphorus is one of those elements that can do that. And let's take a look at the periodic table. Okay, come on. Yes. So there's our phosphorus. Okay. And our phosphorus is in period 3. So across this period, we are filling the p orbitals. And these are the elements. Anything on period 3 or lower, 4, 5, 6, all of these are large enough atoms that they can expand their octet. Okay. If we're in second period, they cannot. But phosphorus can. So this is actually not a problem. Into my backpack. Grab a better pen. I like these pens better. So, with our expanded octet, some very interesting things happening now. That this phosphorus bonded to these 5 things, we're now going beyond the realm of tetrahedral. So all of you have had organic chemistry. You saw tetrahedral structures all the time. You saw trigonal planar structures. You saw linear structures. But not the structures that you must have when the octet is expanded, like we see in this case. Alright, so what happens now? Well, this is what happens now. So instead of tetrahedral, somehow these electrons need to push away from each other as much as possible to have the lowest energy possible structure for this particular molecule. How's it going to do that? You know, with the tetrahedral, they're all pushing each other away in 3 dimensions. And we get, in fact, why don't we remind ourselves what this shape looks like for tetrahedral with our carbon center. And what this this looks like. This is kind of like a Dungeons and Dragons four-sided die, actually. Tetrahedron. And it is similar to that because those dice have four, I guess you call them apex, four corners to them. And if we were to draw a triangle that connected these three, that would be a face of the die. And then here would be another triangular face. And underneath, another one. So that's a tetrahedron. And so this shape here we call tetrahedron. And what is the bond angle? Say this is methane, carbon in the center. And why don't I put hydrogens here? Create these single bonds, carbon, hydrogen, all around. So this is natural gas, methane, the structure. This is the simplest hydrocarbon that there is. And this bond angle, all the way around for all of them, right here, 109.5. 109.5, 109.5, all of them. Perfectly symmetrical in that way. So when you have a central atom and four atoms around it, then that is the most stable structure. That is the maximum that any of these pairs of electrons making up these bonds, that's the greatest distance they can push away from each other and be the furthest away in 3 dimensions. But once you attach a fifth atom, like we're now seeing here, then what? Then what? What is the most stable structure? And that's what we've got here. Okay, so let's build this. This is, I'm trying to decide what colors I want. I think I want to use black because on this kit, the central atom is silver, kind of a gray, and it would blend in with the gray that I used on the methane over there. So let's look at this. One of the chlorines is going to be up top, and one's going to be directly below it. Here's our phosphorus atom in the center. And then the other three, let's see if I can do this so you can see. The other three are 120 degrees from each other in that center plane. So let's put those on and see what this looks like. Right now we're just putting on the bonds, like so. And next, of course, we need the chlorine atoms. The convention with these model kits is that chlorine is green, which goes along with chlorine gas is a green gas, green colored. And fluorine gas is yellow, and so those yellow ones are fluorine, usually used for fluorine. So I'm going to dig around here, pull out some chlorines, and hopefully there's 5 of them. I think there is. And by the way, notice we also have orange orange is often used for bromine, and the purple is usually used for iodine. And neither of those are coincidence, because bromine is a liquid at room temperature, and it is brown, which is sort of like a dark orange, right? And iodine at room temperature is a purple solid. So these model kits are giving a little nod to what these molecules look like in nature, these elements. Okay, I'm almost done. Almost done. All right. Here's our molecule. Here is our phosphorus pentachloride. We've got these two that are in a straight line, and we call this the axial positions. Kind of like this is an axis. We're to spin this around, and if this is the axis, let's see if I can do this. If this is the axis, these two that are up and down, these are the axial positions. Meanwhile, these three, these are all in the same plane, 120 degrees from each other. And these are called the equatorial positions. So if you imagine this is like a globe spinning, and the equatorial would carve out a line. It's like the equator, right? If we're spinning around the axis. So axial, equatorial. And this is the most stable structure for any molecule that has a central atom that has expanded its octet, and it's got 5 atoms around it, bonded to it. So this is according to VSEPR theory, valence shell electron pair repulsion. I'll write that down. Valence. I'm going to bring this down so you can actually see when I'm writing. Valence shell electron pair repulsion theory. Used to predict molecular structure. Okay, so what happens if you have a different molecule? Let me give you another example here. Sulfur tetrafluoride. Sulfur tetrafluoride. Okay, how tempting is it to just simply say, hey, there's a sulfur, 4 fluorines around it, and to just draw the structure like that, or draw the Lewis dot structure like that and be done with it. So tempting. It looks so easy. And you could be tempted to make it tetrahedral, just like this, with sulfur in the center and 4 fluorines around it. But not so. Okay. Why is that? Why are we not seeing this kind of structure here? Well, we need to look at all of the electrons in the molecule. So let's do that. And to do that, we need to not only count up the electrons in sulfur, but also in the fluorines that are there. So let's do that. Okay, so if we have sulfur, and we only have one of them in this molecule, and we have 4 fluorines. Okay, so when we determine how many of our valence electrons we have, we can look at the periodic table and determine that, and then we can multiply however many atoms there are by that number. So valence electrons. Okay, I always have a periodic table handy. So sulfur, how many valence electrons? All right, let us just count over for this period, and we see that there are 1, 2, 3, 4, 5, 6. So we've got 6 valence electrons. And there's 1 sulfur, so let's go 1 times 6 equals 6 electrons. Okay, fluorine. We know that there's 4 of them. So we will multiply 4 times what? Let's see. Periodic table. We'll count over in this period. There are 1, 2, 3, 4, 5, 6, 7. Okay. 7. So we've got 4 times 7 is 28. Those are all the valence electrons that fluorine is contributing to all the bonding that's there. Now we add these up and we get 34. These are all the valence electrons in the molecule. My dog has just joined us. And he's just staring at me. Oh my gosh, what does he want? If I can get him in the camera, I will, because I think you'd enjoy it. He's a corgi and he's very cute. Okay. So this is the number of valence electrons that we have in this whole molecule. And we need to distribute them. And the way that we distribute them is, first, we have drawn out the skeleton structure of this molecule. We've chosen our central atom. Central atom is always the least electronegative atom. It is the least electronegative, and so it is the most, I'll anthropomorphize the central atom here when I say it's the most willing to share electrons. Our electronegative atoms are more stable when they're pulling in and have more electron density around themselves, whereas less electronegative are just fine by sharing the electrons. So our sulfur, less electronegative than fluorine for sure, fluorine being the most electronegative atom on the periodic table. So our fluorines are on the outside. And so now when we are distributing these 34 electrons, we are going to put them in the bonds, of course, first, and then put them on the electronegative atoms. And then we'll see what happens, because there's some different possibilities that can occur once we've used up all those electrons. So, let us begin. We've got 34 total that need to be accounted for. And so far, 2, 4, 6, 8 are taken care of. And now we're going to distribute the remaining 34 around the molecule, starting with the peripheral atoms, those electronegative, electron hog fluorines. All right, so 2, 4, 6, 8, and so now 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, can you see what's happening here? We have now accounted for 32 electrons. But there are 34. So where is that extra electron pair going to go? And there is only one place, and that is on the central atom that can expand its octet. Okay, so remember what I said a little bit ago, that these period 3 elements, these can expand their octets. We saw that phosphorus expanded its octet, and so can sulfur. And that's exactly what has happened. And so we will put that extra electron pair right in here. We're just going to nestle it in to the sulfur and put it in there. Okay, so now what? In terms of, we're going to go back to the molecular models. What does this mean? What is the shape going to be for this molecule? So we first look at the total number of electron pairs that are around the sulfur. And we see, just like with phosphorus, had 5 electron pairs that were in bonds, sulfur still has 5 electron pairs. 1, 2, 3, 4, 5. But notice how 4 of them are in bonds and 1 of them is a lone pair. So it's a little bit different in that sense. But we're still going to use this central atom that has 5 electron pairs around it. Now, those pairs are either bonded or a lone pair. And in this case, notice how I removed one of those bonds because we have just 4 fluorines around the sulfur. But this location is still being taken up by a pair of electrons. But there's not a nucleus there. Here there's a fluorine nucleus, and yes, I still have the green on there. They work just the same. The colors are just convention. So I'm not going to swap out the green for the yellow to show this. Okay, so we end up with this very interesting shape that would be totally unexpected. Look at this thing. It's lopsided. It's this asymmetric kind of thing. Look at this. It does not look like a tetrahedron. These 4 fluorines are asymmetrically surrounding this central sulfur. And there's lone pair right there. This is called a seesaw. Because if you imagine, if this is the ground here, my hand, this is the ground, and this is like a teeter-totter, like a seesaw. Also sometimes called a sawhorse. Teeter-totter, seesaw, sawhorse, one of those. I just put on the paper here, I can also do it like teeter-totter. Okay. So here's the question that you might have. That's a very good question. And that is, Professor K, why the heck did you take it off of the equatorial position? Why did you not take it off the axial position? See, I could have done that. I could have had it be this kind of pyramid shape, like that, instead of the teeter-totter. Right? But no, I took it off of the side axial. And there is a very good reason for this. I'll show you both scenarios, but this is never observed where the atom comes off of the, or I should say when you have 5 electron pairs where 4 of them have atoms and 1 is a lone pair, you never see this structure because this is less stable than the seesaw. And the reason why it's less stable, actually let me keep it like this. Imagine if there was, if this did exist and there was a lone pair here. This lone pair would be interacting with 3 bonds at this kind of 90-degree angle. It would be in close proximity, 90 degrees, if we imagined that these electrons were right here, this electron pair. It's interacting with 3 of them at 90 degrees. That's a significant amount of electron repulsion that's happening. So what about when we take it off of the actual place where it goes, off of the equatorial position? Okay, so now we've got electron pair that's here, and its closest neighbors, if you want to call them that, are just these 2 bonds that are at essentially 90 degrees from this lone pair that's right here. So there's less repulsion when the lone pair is in the equatorial plane. So this is why this structure is the one that is always seen for this scenario. All right, cool. So there's some model kit action. I really like this kit by Mega Molecules. They do a good job. All right, and what next? We can do more of these if you want, but I'm gonna swap it out and try something else. I'll put some of these away. Get our little pieces over here. And break up our bonds. this is really good for learning, but it's also good for sleeping. So if you're having trouble sleeping, I am here, spot on for you. Just the gentle droning of science topics might just be the trick. So I am glad to do that for you. Okay, I'm gonna move my model kits, and I'm gonna try something that I've never done before, actually. And I had this idea because there are a lot of ASMR videos of people crumbling up gym chalk, which is kind of goes in that so satisfying category, and it sounds really cool. It looks cool, and I actually recommend trying it, like doing it, not just watching it. Because when I got some of that gym chalk and did it, I have on my YouTube channel, and it was great. So I think everybody should try that at least once. Of course, if you go to the gym and then you grab some of the chalk and you start squishing it up, they might not like that. But it's not too expensive if you want to get some. Just saying. Alright. So I'm going to get, I have a cutting board, and I might need to make room for it. I think it'll fit, actually. Okay, get all this stuff. Okay, hang on. It's right back here. And yes, I have a cutting knife. Okay, here we go. So, gym chalk. I don't know if it always comes like this, but when I bought it, I just ordered it off of Amazon. It arrived like this, in these adorable little Christmas or birthday, Hanukkah presents. I don't know. It's like these little gift boxes almost. So, here's my gym chalk that's wrapped. So we can unwrap this thing. And here it is. Okay. So here's our gym chalk, and along with just being so, it's very soft and it's very light. It's got some amazing chemical properties as well. So calcium carbonate, is this the actual ionic compound, and calcium very abundant on the planet, and as is carbonate. So carbonate is, oh, it's so smooth. Carbonate is in many, many rocks, and we also find it in natural waters, and it's also in our bodies to a significant degree, mostly in the form of bicarbonate. And bicarbonate, that's also part of baking soda, sodium bicarbonate. So this is very abundant, and it does some pretty magnificent things on planet Earth. Carbonate acts as a base. A base is something that can accept a hydrogen ion, and by doing so, it can help alleviate when there is acidification of natural waters. And so, of course, that is an issue with global warming, or along with, I should say, greater amounts of carbon dioxide that are in the atmosphere that can then dissolve in the water, creating carbonic acid and causing acidification. But if there's also some extra carbonate in the water, then that can help offset that reaction and can help buffer some of that acid. So lots of really cool things. Oh man, and the biochemistry that happens in our bodies, it's really cool too. Okay, so just a little bit of the chemistry of our calcium carbonate, or gym chalk. But this is what I wanted to do. I was curious, what is it like to slice it up? So I've crumbled it, and that's cool, but can we slice this? What's this gonna be like? So let's try it and see. Is it going to just shatter, or is it going to crumble, or is it going to be like a thin sheet? And I don't know. So let's see. It was definitely squeaky. Did you hear the squeak? But it made it very smooth. Oh, I like it. Okay, so that was trying to do a sliver off the side. Alright, let's do a bigger chunk and see if that makes a difference. Definitely squeaking, and now it's definitely falling apart, just kind of crumbling. And see this time, it didn't just have that smooth thing. It had this kind of chunk fell out. So what's really interesting about these macroscopic sculpture, or, well, I guess you could call it a sculpture, kind of, but these macroscopic structures that we see, like how table salt. Have you ever looked really closely at table salt and noticed that it's like a cube? that is direct reflection of what the structure of table salt is on the molecular level. My corgi is pacing. Oh my goodness, he just keeps looking at me. I'm gonna have to show him to you. Okay, let's see if what's the easiest way to do this. Okay, I think we're gonna turn. Let's see, this camera might work better. Oh yes. Okay. I can't tell if you can see him. Hang on. This might be the best way to do it. Okay. There he is. Neil. He's checking out the gym jug. Looking at the gym jug. Let me move this out of the way. Let's see a little bit better. Alright. Well, this is Neil. You've now met Neil. Meal time. All right, that was a fun break that I was not expecting. So very fun. All right, cool. So, one of the things about, just looking at any rock, and you can also think about like quartz and how they're angled, or if you get try to think of like other gemstones and things like that, and how they naturally exist. Those shapes that you see, those are essentially, those are reflecting the shape of the actual molecular structure. Now, something like this isn't going to naturally crack in the exact shape of the ionic structure of calcium carbonate, because I believe this is essentially a powder that's been like crammed together. This isn't a big crystal, not a one whole crystal. It's a whole bunch of tiny crystals that have been smushed together to make the gym chalk. So I kind of like this, doing it this way, like this, just sort of shaving it off, That's kind of satisfying. I'm not really a fan of the squeaking, like cutting it through and it's like squeak. I feel like I could do this for maybe a little bit too long. So there's our gym chalk. I'm kind kind of tempted to crumble it, but I'm also I can't have powder flying everywhere either, so. But I did make on my ASMR chemistry YouTube channel, there's a whole video crumbling the gym chalk, and I talk more about chemistry of calcium carbonate, and then we do a little chemical reaction. Okay, cool. I'm not even kidding, I could do this. I could do this for, I don't know, a long time. It's so smooth, look at this. That's really smooth. Okay. And then just have this really nice soft powder here. It's left. It's like, it's so soft. When I touch it, I almost can't feel it. It is really soft. That's cool. Okay. All right. Well, there's my little gym chalk cutting experiment. So thank you for partaking with me on that journey. I really enjoyed it, actually. All right, cool. Let me move this for a second. This is what I have next. So I've got this quite a long time ago, and this is a box that's got just so much beauty in here, beauty, knowledge, all sorts of stuff, and it's fun to look through, and let's do that. Let's take a gander at what we have in here. So it has all of the elements. Now, we are not going to go through them all. Wow, I wonder how many hours I would be here if I did that. But we will look at what we do have. There's absolutely beautiful photos on this, and I'm gonna move some things so we can see a little bit better. Let's see, I'll put this here. notice how this first one here, hydrogen, it's got photos of outer space. And these are nebula that are shown here. And the reason for that, so this is a little bit more, I almost feel like these are tarot cards or something. I'm doing a tarot card reading with elements, maybe. So much of the space consists of hydrogen. Hydrogen's the most abundant element in space. And so it's fitting that we're showing stars here with hydrogen. And so just like on the periodic table, they show this number 1 is showing what's called the atomic number, and that is how many protons are in that element. And then this is the atomic mass, which includes the average mass of all the different isotopes of hydrogen. Oh, that's interesting. Oh gosh, do I have gloves? I will have to get some from the chemistry lab. I'm trying to think if I have any. I'm not sure. I will look. I will be right back. Okay, well, I did my best to look, and I don't have any here, but I do have boxes and boxes of them in the chemistry lab that I can get for next time. So thank you for that request, and that's great to know, because I do know a lot of people like gloves, so you can get this. Okay, awesome. So these cards, they've got all, basically anything you would ever want to know about these. And it does say that 75% of the universe is hydrogen. So, totally makes sense. They show that. And helium. Helium's got this picture because just like neon, and just like krypton, you can fill helium up into tubes and you can have them glow like this and not worry about them blowing up like if you had hydrogen in them, since hydrogen is flammable. So it is very inert, and you can see them in things like those glowing signs. I should get glowing signs. I should have them behind me. atoms is lithium. And lithium, best known as, or I would say it's best known as, used as a pharmaceutical, as an aid for anxiety and things like that. So, very helpful for a lot of people. And a lot of these, lithium's a metal, and beryllium is a metal. All of these look really similar. They're all shiny. So it's hard to tell them apart. So you have to test them by their reactivity and things like that. And even boron, semi-metal, but it still's got that kind of silvery look. And then everything changes. We get to carbon. And carbon is a non-metal. But carbon by itself, it can be a diamond, like that's shown here. But it can also be graphite, like my pencil, carbon, just a different form of it. So these are called allotropes of each other, diamond and graphite. The carbon atoms are bonded a little bit differently from each other. Carbon in diamond has this tetrahedral structure, but instead of, this is methane here, instead of these hydrogens, there's carbons, and then there's another carbon, and then there's another carbon, and they're all in this tetrahedral configuration with each other. Nitrogen is so much fun to play with. Okay, I'm not sure if you can see this. I feel like it's hard for me to tell if it's in focus, and but hopefully it is, because you can kind of see it's bubbling. So this is showing liquid nitrogen, which is dangerous, but it's really cool. So you can make liquid nitrogen ice cream. You can make ice cream really fast with it because it's so cold. But you have to be careful, because say if you were to stick your finger in it and hold it in there, your finger would freeze and then crack and fall off, literally. So you have to be super careful with it. But you can do some super fun things with it, like putting a flower into it and then pulling it out by its stem and then shattering it. Things like that. It's just really fascinating. Really fun. So, everyday life, we don't get to see nitrogen as a liquid, but you can get it. I don't know if you need to have like a license, or I'm not really sure, but since I work in a chemistry lab, we have liquid nitrogen all the time. It's pretty much any time I need some, I can get some. But it's not really a normal everyday thing. But it is in 80% of our atmosphere, so gas nitrogen, yes, everywhere. And oxygen, 20% of our atmosphere. But look at this. This is a picture, this is a photo of a bowl. So it's a metal bowl. That's what that this border is. And we're looking at this blue liquid. Oxygen as a liquid is blue. Isn't that amazing? And just like with nitrogen, that's really, really cold. Really cold. Oxygen also, when it's liquefied, it has to be really cold. And it's also can be explosive. So again, you have to be really careful with it. I've only seen, or I should say heard, a liquid oxygen explosion once in my life, thank goodness. Yeah, a little bit scary, but so beautiful. All right. And then fluorine gas. It's a really light yellow, but you can't see that in this photo. But really reactive. We don't see this in everyday life because it's so reactive that it just reacts with other things and makes new molecules or compounds. So, all right, and then I think I'm going to stop here. But neon, so neon signs, right? Because neon is very unreactive, just like we saw with helium. So these two elements, similar to each other on the periodic table, they are in the same column, in the same group, because they have the same reactivity, which is not very reactive. So these are two of the noble gases. They're gases at room temperature, and I guess they're called noble because of their unreactiveness. They don't change. Very difficult to get them to change, to react. So that is a little bit, just a little bit, because look at this, we have so many cards. So we just saw a little bit of this deck. Look how many there are. Okay, we're going to go to the very end. Check it out. 118 is the last element. And when I got this deck, this element had not been named yet. So look, question mark. It has now been named. So I guess I need a new deck. I'm not sure. Or not. Or maybe this is the vintage deck that will sell for a lot of money on eBay someday. I don't know. Alright, so there's some extra, I don't know what these are in the back. I've never looked at them before, actually. Oh, wow. Oh, but this is interesting. Okay, hang on. Hang on. Hold the phone. This card here. Elements sorted by various properties. Percentage by weight of the human body. So, element with the atomic number 8 has the greatest percentage in terms of mass in the human body. Do you know what element that is? Atomic number 8 means there's 8 protons, and that corresponds to oxygen. And second most abundant by mass is carbon. This is just in terms of elements. So if we were to talk about molecules, what is the most abundant molecule in the body? Most people know, but if you don't, it is water. Speaking of water, I'm gonna drink some. This card also says percentage by weight of the Earth's crust. And guess which element's number one there as well? It's also oxygen. And then percentage by mass in the universe as a whole. And as I said before, hydrogen is number one. Anyway, I didn't know this was here, so I'm kind of excited. Interesting. All right, cool. Very cool. All right. I think it's time to light that candle. The candle that I was worried about it being annoying. I don't know. You know what? It's so hard to say, especially with ASMR. Like, first off, some people hate ASMR. They find just ASMR in general annoying. And then, within ASMR, there's some people who like some things, and they don't like others, and, you know, it just totally depends. And so, some people might like this wooden wick candle, and some people might not, and that's okay. So, let me get these all straightened up. Okay. Alright, so this is the deal with this candle. Get this over here. So notice how there's the wick. And notice how it's a line. So this is not just, you know, a lot of times they're a piece of cotton or some kind of fabric or something. And notice how this one is flat. So it is a thin piece of wood. And so when you light it, instead of just the slow burn like these kinds of candles that burn pretty quietly, this is a little bit different. So if you haven't seen this before, you can check it out. So I need to light this. Oh, I guess I do have a lighter, but we're going to do it this way. I use my splint. It's kind of a chemist kind of thing to do. Oh, there it goes. Okay. Alright, can you hear it? Let's see if you can hear it. I'm going to bring it a little bit closer to the mic. So for me, I really like it because it reminds me of being out in the woods and building a fire, and it's sort of that crackling noise that wood has. So that's the part of it that I enjoy. But I tried making an ASMR video about 1.5 years ago with it, and it was so loud that you couldn't really hear anything else. So I don't know. I'm not sure. I'm not convinced that it's the best ambient sound. Here's my periodic table deck. All right. I am going to move this so I can see you a little bit better. Okay. All right. I am going to say good night for now, and or goodbye or good morning, depending on where you are. And hopefully you either learned something or you were able to calm down and relax, or even better, that you were able to sleep. And I am here not only doing ASMR, but I do regular chemistry sessions too. So ChemistryRockstar, I am on Mondays, every Monday, so it's on my schedule. And I'm also doing Wednesdays as well. And right now it's a Friday, so maybe I'm on a Wednesday, Monday, Wednesday, Friday schedule. But I'll also be popping in between. So you'll be able to find me at various points. And if you follow, then you'll get notification when I'm on. So I would really appreciate your follow. If you could do that, I would thank you. So thank you in advance. All right, well, have lovely hours to come, and I will see you next time. Thank you. Thank you for joining me.